Uh, okay, continuing on to the second page. At the top here is presented the formula for the tangent plane again. So this is the same formula as I've presented on the previous page. However, if you look at the way the normal vector is written here, this vector is the negative of the normal vector I wrote on the previous page. But in the end, the normal vector and its negative are both orthogonal to the tangent plane, so either can be used as the normal vector. Okay, so that's the tangent plane. And one additional thing that we can do is we can take the normal vector to the tangent plane and extend it to an entire line. So by just taking the normal vector as the direction vector of the normal line, and the point on the normal line is given by the same point as previously, right? So this point that connects the tangent plane with the graph of the function. So it has coordinates a, b, f of a, b. So taking this information, you can write down the parametric equations for the normal line as follows, right? So the point again is given by a, b, f of a, b, and then the direction vector is exactly taken to be the normal vector of the tangent plane. So essentially visualizing the tangent plane together with the normal line, right? So here, say you have, so in yellow here is the graph of some function. In blue here is representing the tangent plane to this graph at this particular point. And the pink line that's going through the tangent plane like this is the normal line, which is orthogonal to both the tangent plane and the graph at this point. Okay, so now we want to take this information here and take a look at example 1, where we're asked to write down the equations of the tangent plane and normal line to this function at this specific point. Okay, so the first thing you should notice in this example is, so this is the given point, right? So the coordinates a and b in the formula are exactly 2 and 1, and also the z coordinate here, 13, is the z coordinate of this point, right? So in the formula, it's given as it's calculated using the original function, right? So if you take a and b and you plug it into the function here, you'll see that it's exactly equal to 13. So that's already been calculated for us, right? So f of 2, 1. Let's just calculate it real quick, right? So x cubed, so 2 cubed plus y cubed, so that's 1 cubed, and then plus 2 squared over 1. So calculating this is 8 plus 1 is 9, 9 plus 4 is 13, right? So again, in the formula for the tangent plane, it's written as the function value at the point, but this is also the same as the given z coordinate, right? So this part of the formula is already calculated for us in this problem. Okay, so in any case, let's determine the rest of the tangent plane. Right, so we need the two partial derivatives with respect to x and with respect to y. So let's first calculate the partial derivative with respect to x. So here we're thinking of y as being constant. So the derivative of x cubed is just 3x squared. Y is a constant, so this whole thing is a constant. Derivative of a constant is 0. So this term goes away. And then the last term, 1 over y, is the coefficient. So the partial derivative doesn't do anything to the 1 over y. and then the derivative of x squared is just 2x. Okay, so this is the partial derivative with respect to x. And so for the tangent plane, we need to plug in the coordinates a and b and calculate it at this point, right? So let's do it now. So a is 2 and b is 1. So we plug those coordinates in. So we get this. And just calculating this, this is 4 times 3 is 12. 12 plus 4 is 16. Okay. Now we need the partial derivative with respect to y. Now we think of x as being constant. So this is a constant. The derivative of a constant is 0. So this term goes away. Derivative of y cubed is 3y squared. And then finally, the last term here. So I want to take, I'm thinking of x as being constant and taking the derivative with respect to y, right? So I'm going to think of this as x squared y to the minus 1. So then I can just use the power rule. Right, so x squared is constant, so the derivative doesn't affect the x squared. And then here I use the power rule, so the minus 1 comes down. So instead of a plus, this is a minus. And then I subtract 1 from the power, so negative 1 minus 1 is negative 2. Okay, so let's just rewrite this. So we get 3y squared minus x squared over y squared. Okay, so that's the partial derivative with respect to y. And then similar to before, we calculate it at the point AB. So just plugging the values in. So 3 times 1 squared minus 2 squared over 1 squared. So what is this? This is 3 minus 4, which is equal to negative 1. Okay, so that's the partial derivative with respect to y. So now we have all the pieces of information, right? So so we want the tangent plane first. Right, so z equals, so the coefficient of x is the partial with respect to x, so which we calculated with 16. And then this should be minus the x coordinate, which is 2. And then the partial with respect to y is minus 1. And then the y coordinate was 1. And then plus the z coordinate, which is 13. Okay, so that's what we get as the tangent plane. And now we're also asked to write down parametric equations for the normal line. So let's do that here. So if you remember, the same information goes into the normal line, right? So the coordinates of the point is the point for the normal line. So so the x coordinate is 2, and then the coefficient of t comes from the normal vector, right? So which is this, and then this, and then minus 1, right? So we get plus 16t for x, and then y is the y coordinate was 1. And then the partial with respect to y is minus 1, so it's 1 minus t. And finally z is the z coordinate was 13. And then we always take, so if I take these two as being positive, then this should be a minus. So this would be a minus t. Okay, so that's the parametric equations for the normal line.